Welcome, everybody. I would like to welcome you all to this joint webinar between the EMEUNET Visibility and Global Affairs Subcommittee and the Grappa, the Young Grappa representation. Today, we're going to talk about a very important topic. The title is From Promise to Practice, Making AI Work in Rheumatology. My name is Emanuele Bozzalla. I am a rheumatologist from Italy. I am current member of the EMEUNET Visibility and Global Affairs Subcommittee. And throughout this session, we will try to have an overview on how AI application could be exploited in real life. So we will have some practical cases, both in research and in clinical aspects and clinical settings. And we will then move on to a second aspect, very important as well, which is which barriers are present nowadays in implementing AI properly in the health system and in our daily practice. Before getting started, just a few housekeeping rules for everyone. So I would like to ask you to turn off your camera and your microphone, as this webinar will be recorded for future viewing. If you have any questions for our speakers, please just write them down in the chat and we will go over them at the end of the webinar. Both sessions will be one next to the other and we will just take all the questions at the end. During the question and answer section, however, just please feel free to raise your hand button and you can also ask directly question to our speakers and panelists. At the end, but we will go back to that later, please do not forget to complete the evaluation survey. So we can now move on. It's a pleasure for me to have here as a co-moderator for the third time with Young Grappa, Andre Ribeiro. So it's my pleasure, you can take the stage.
Thanks, Emmanuel. It's a real pleasure to be here representing Young Grappa, as you said, to join forces in our third joint webinar. And without further ado, I would like to introduce Sergio Del Vescovo, who is a researcher in the University of Bari. And today he'll be talking about the application of LLMs or large language models in clinical and research settings. Sergio, the floor is yours.
Okay, thank you, Andre. Thank you, Emanuele, for the presentation. And good morning to everyone. So today, as already told by Andre, we're going to see some things about large language model. We're going to move into three main topics. Firstly, we're going to consider how large language models work briefly. Then we are moving to how to interact with large language model, so prompt engineering. And then we're going to consider also applications for clinical use or also for research use of large language model. So firstly, I think it is very, very interesting to understand a bit. I know it's difficult, I know it could be difficult, but it could be very, very interesting to understand how large language model works, because they are very incredible statistical machine. So, when you input text, for example, in your ChatGPT in Claude, you input a sentence like this one you can see on the screen. I want to understand theoretical this mechanism. And this sentence is firstly broken into fragments. So this process is called tokenization. And this token then receives a numeric ID. Then we have stage 2, which is the embedding. So each token becomes a vector. So typically 1024 dimension. And this token codifies the semantic properties of this vector, codifies the semantic properties of each token. Also, the positional information, anyway, is very important because, for example, the sentence dog bites man is different from the sentence man bites dog. And so, also the positional information of each token in each sentence should be added. So in the end, we will have this final vector, the token plus the positional information. Then we have the core, the LLM's brain, which is the transformer layers, made up of 12 to 96 or more layers, where each layer uses this process, which is called multi-head self-attention, that allow to understand the connection, the context of each token within its sentence. So the connection, the relationship of each token with the other tokens. And in doing this, so for each token is created three new vectors are created. The vector query, which codifies what the tokens is asking for, the vector key, so what other tokens offer, and the vector value, which is the actual information carried. So after this phase, each token passes through its feed-forward network for reprocessing, so for complex pattern processing. And this architecture here is repeated then a lot of time for each layer. In the end, so we have the final layer that has each token representation in its context. And so this final layer projects each token onto the vocabulary of the model. You know, each model, ChatGPT has a vocabulary, and for each word in the vocabulary, numerical scores are assigned. Higher scores, higher are these scores, higher are also the probabilities the word should be considered in the large language model response. So, you know, these scores are then converted into probabilities with a transformation, a softmax transformation, and the model in the end samples from this distribution to select so the word generated in its response. So this is briefly, very, very briefly, how large language model works. So as I have already said, they are very incredible, powerful statistical machine. And anyway, the more recent models use also a more recent architecture, which is very, very fascinating. Also this, it's called the mixture of experts, because instead of having one giant brain, they have very different sub-specialized networks. So when you ask a question, for example, a medical question, first you have a getting network that analyzes it, and then it will activate only your specialization of interest, for example, the medical reasoning or the scientific knowledge. And this will have two advantages, obviously. Firstly, efficiency, because you run your large language model using it faster and also being cheaper to run. And also you will have more accuracy in your response because it will be more specialized. You will using only the sub-specialized networks relevant to your query, to ChatGPT or Claude, for example, leaving also the others sub-specialization dormant. But when you're using also large language model, you can set them. You can set how they generate your response using several parameters. The most important one, the most used, is temperature, that control the randomness of your responses, of generated tokens. While we can set also the top key of the top P. The top key is codifies the choose among the key most probable tokens. It will mean that if you set key to 40, for example, the model will choose your words among the 40 highest probability words or tokens, maybe better. Or also the top key, or the top P, sorry, which limits the selection to the smallest set of token was cumulative probability exceeds P. So clearly, if you have a low randomness of generated tokens, for example, if you have a low temperature value, this will give you more deterministic response. And this could be good for medical questions. While if you want to increase creativity, randomness of generated tokens, for example, for brainstorming, you set high temperature value. But how you can set these parameters, so how you can set temperature, you can do it using an API when programming, or also more easily using graphical interface, such as that one on the right figure in the slide. This is a graphical interface in the console of anthropic.com. And here we can see an example. So we asked to the model, what are the classification criteria of rheumatoid arthritis? And you can see the response here with a low temperature value, the 0.2. We have obtained so a deterministic response, a scientific response. While if we set high temperature value, a T of 0.9, we will obtain a more creative response, a more narrative one, filled with metaphors, metaphorical expression that in this case, you know, could be not the best appropriate response. So in this case, for medical question, temperature should be usually set to low level. But when using large language model, and this is very, very, very critical, very crucial nowadays for researchers, also for clinicians, It's very important also to set correctly your questions, your query to large language models, and so your prompt. And because of this, prompt engineering nowadays is a science of structuring your request to the large language model. And so this is because the difference between a vague prompt and a well-engineered one can be very, very crucial, especially in reproducibility, and so in obtaining consistent outputs for researchers and clinicians. And this is very, very important. And so we're going to see some of the several prompting techniques. From the easiest one, you can, when you're using a large language model, you can simply ask your task. You can simply ask your query to the large language model, and that is called zero-shot prompting. But you can also ask your query, also inputting an example in a way that the LLM may also address your response. But also you can use 3 to 5 examples, and that is a few-shot prompting. This is very, very useful. This could be very useful in order to address the LLM response. And also, it is very important that when you're writing your prompt, that when you're writing your examples, you should include edge cases in a way that your large language model could be able better to handle unexpected input. Then we have this one, system contextual and role prompting, which are very, very important and very useful. System prompting, in plain words, could define the big picture of your prompt. So it gives, it assigns the overall context and purpose for the large language model, while the contextual prompting has background information relevant, so details relevant to the task you ask to the large language model. Also, the role prompting is very, very useful and very frequently used, assigns to the large language model a specific role. For example, assigning a task to ChatGPT that should analyze from a point of view of a rheumatologist is very different to ask him to analyze that situation from the point of view of a neurologist or a lawyer. So assigning specific roles could be very, very, very critical, and could be very useful in obtaining the more accurate response. But you can use also all of these 3 together. So system contextual and role prompting in order to set how the LLM should behave, what to focus on, and also what perspective it should adopt. Another possibility also is a setback prompting. So firstly, you can ask to your model a general question, and then after that, only after eliciting general principles, you can ask your specific desired question only after eliciting general principle, and this will increase surely your accuracy in your response. One of the most used anyway is this one, is the chain of thought prompting, because you can also ask to the model to solve your task, to solve your problem using intermediate steps. And it could be useful in particular when you're asking to solve math tasks. You should all know that LLM are not so brilliant in math. And also when you want also to learn from the reasoning steps of the large language model. Generally, we can say that every task that can be solved by talking through, it could be a good candidate for chain of thought prompting. But also we can generate different chain of thought responses. And so when you generate different chain of thought responses, then you can select the most consistent answer, always in order to increase the accuracy. And for increasing complexity, for handling complex tasks, you can use this one, the tree of thought. So your LLM may generate, in this case, multiple paths. It will evaluate each path, select the optimal one, and then it could also have the ability to eventually backtrack if a path proves suboptimal. In the end, though, finishing so with the prompt engineering section, I think it is very, very important when you're prompting, when you're using large language model, to set constraints, because this is very important to achieve reproducibility, and this could be very essential for clinical workflow. So you should set structural constraints, content constraints, style constraints, and especially specifically boundaries, in order to make the model to stay grounded in provided fact and not inventing information. This is essential, especially to reduce hallucination, because hallucination when using LLM are very, very critical problem. And so you could reduce it a little bit, putting boundaries to your prompt, to your large language model. But here now we move also to possible application in 2025. You all know that LLM usage can be defined as pervasive, especially in the academic world, as you can see here. Their use is very, very, very common, especially in writing, editing, and grammatical correction. And that could reflect their nature of text generating support. You should consider them text generating support, not educated researcher. And as text generating support, so as support, they can support you in writing abstract, in creating abstracts from embedded to paper, using, as you can see here, all of that prompting technique that we have considered before. So RAL system contextual prompting. Also, you can instruct them with constraints. Also, you can use chain of thought prompting. You can instruct them to follow the abstract submission guidelines for a specific congress. Also, as you can see here, we can use them to summarize research literature. So they could be very important to recover time. You could embed your work in your prompt, and then with the accurate prompt, they will give you a well-structured summary of your paper, and they will make you recover some time. But they could be very, very potential. They could be very important also for diagnostic and educational purposes for patients. And that is where RAG, which is an acronym that stands for Retrieval Augmented Generation, may come in help. So instead of relying only on what the large language model could remember from their training data, RAG could recover information, so could connect the model to trusted live sources, such as clinical guidelines, drug databases, even your hospital electronic health records also. And so in this way, firstly, they will recover the relevant information, the relevant content, and only after that, they will give you a response grounded in that material. And that means, so less guessing, fewer hallucinations, and that is very, very important. I repeated it. We have to try to reduce hallucinations when using large language models, and also more clinically valid outputs. So now one of the, I think, most fascinating potential of large language model, we can use them to compute disease activity scores and so kinematic indices, helping us with kinematic evaluations, especially in diseases where these structured assessments can be very, very difficult, such as myositis, so inflammatory idiopathic myopathies. And so for this reason, we tested whether Claude could replicate human expert assessments in the MDAT-VAS scoring. And how did we do that? So we use a prompt engineered LLM, giving him also clinical documentation, including muscle weakness patterns, extramuscular manifestations, and also physician global assessments. And so we achieved an ICC of 0.93 with strong correlations also with experiences assessors. So as you can understand, in this case, we were inputting only text, only informations in a text modality. But nowadays, multimodal LLMs are critical and are very, very, very usual to use them. So you can input nowadays in LLMs images, audio, video, not only free text. And as you can see in the figure, so we have, when using large language models, modality encoders which are like translators that can communicate into different native language. And then they will talk each other with the common language, such like English. And then this information that will be in a common shared embedding space in numerical vectors will be elaborated by the LLM score, so the transformer layers we have discussed earlier. And then output projectors and modality generators will generate your output in your desired format. So you could obtain also output in different formats, like images or video. And for this reason, we tested these multimodalities of large language models. Also with Claude version 3.5, we tried to test its performance to score with the CDASI skin scoring, always in dermatomyositis scoring. And in doing this, so we gave to Claude clinical photographs of dermatomyositis skin, and we tried to test its potential, so its capabilities to score with the CDASI score. And in doing this, we achieved also a good ICC, always of 0.92, but actually the performance were different. For very visible features like periangular vasculitis, we achieved good performance, while for subtle or subjective signs like poikiloderma or also chronic skin damage, the performance dropped a bit because eventually for this information, it could be better tactical examination or a more accurate view than maybe the LLM could not achieve better. And so the most important thing anyway from this study was that the LLM was 93% faster than experts. And so this could make this application very, very useful for trial screening, best scoring for multi-center studies, also for screenings of large numbers that then the human may verify. And another thing that you can perform, and this is very, very nice to do this, is to perform a sentiment analysis using large language model. Sentiment analysis is a technique that detects the emotional tone in natural language, if this is positive, neutral, or negative. And for this reason, we tested the sentiment analysis technique in free text responses of patients, achieving so a linear separation between fibromyalgia patients on one hand and inflammatory and degenerative rheumatic diseases on the other hand. So it seemed to us that it's not just what the patient says, but specifically how the patient says it too. And so for this reason, we achieved this separation, analyzing not only the linguistic style, but also the emotional style using sentiment analysis. And so exploring the potential of a new biomarker, you can think to it as a textual biomarker. And also in order to explore the potential of these textual biomarkers, we tried to perform a sentiment analysis on Grappa responses about a survey regarding patients with difficult to see PSA. And so we evaluated the response using Ekman's emotion theory and also Russell's emotion theory, seeing that the most dominant emotions in these patients were sadness and fear. And also multi-domain involvement was strongly related with more negative valence, so more negative emotions. And specifically, axial disease was related with the emotion of fear. Anyway, to conclude, I think it is very, very important to consider one of the most critical points, that when you are computing, clinic indices, or also you are performing your sentiment analysis, you have a problem when you use third-party commercial LLM. You could have a problem with your patient privacy. And because you're not committing a problem from an ethical point of view, you're also violating privacy regulations such as GDPR. And so in order to solve this, you could use this software here, which is LM Studio. And on it, you can run your open source local large language model, which you could run it on your own personal computer without using external servers. And so this is very important because then you can compute your kinematic indices, you can evaluate your sentiment analysis on your patient data without having any trouble with privacy regulation and with privacy of your patient data. And so that's it. Thank you very much for your attention. Thank you, Andre.
Thank you. Thank you very much, Sergio. Thank you for the great presentation. I think you gave us a lot of hints and suggestions for practice, and for me, it was really illuminating. We can now move on to the second part of the section. So we will move to the AI pitfalls and barriers for implementation. And I think we cannot have a better presenter for this part than Xavier Michelena. He works for the Catalan Health Service, where he holds the position of clinical informatics leads for the digital health strategy of Catalonia. So I think really this is a great opportunity for us Thank you, Xavier, for joining us today. Please, the stage is yours.
Thank you, Emmanuel. Just to confirm that you can see the slides.
We do.
Perfect. So thank you for having me. For me, it's a great honor to be back in EUMEUNET. And I actually will start with that. This is Copenhagen 2022. This was the EUMEUNET meeting at that time. It's difficult to spot me because I'm a bit hidden there, but I'm there. And also with me was the, well, elected EUMEUNET president, which is Diego Benavent. And I'm telling you this because at that time, Diego and myself had just started a master in data science and artificial intelligence. And at that time, ChatGPT didn't exist. I mean, obviously, the model itself, GPT, the transformer architecture was already developed, but it was not mainstream. I mean, ChatGPT was launched in November 2022. So at that time, we were convinced by someone that most of you might know, which is Vincenzo, that we had to get into AI, get into coding, get into all this. And I think it was a wise decision because obviously now this has hit us very quickly, and we are trying to see how we implement it in clinical practice. And this is what I'm going to center my talk today. I think it's relevant. Everything that Sergio has explained is really good and is really helpful. But we need to know at each moment and each time how do we use this technology, especially if we have patients in front and we're using patient data. So you might think, what does a rheumatologist do right now in clinical informatics? So I've basically switched my career to solely clinical informatics, and I think this is also relevant to understand the talk today. So this is basically more or less my career as a rheumatology and how I got into coding. So basically, when I was a resident, there was a quite old consultant that was an expert in SPSS, which is a statistical software, and he explained me a few tricks on how to do statistics with that. Then I went to Leeds, to the UK, and started to play around with data, got in love with coding. I had to do some complex analysis, so I had to get into that. Then obviously I started getting into more traditional machine learning models. I trained a deep learning model in MRI, in sacroiliac joints MRI. I did my PhD. I actually did my PhD in axial spondyloarthritis and psoriatic arthritis, so it's also relevant today with this young Grappa meeting. I actually said in my PhD that we should lump spondyloarthritis. I'm sorry, young Grappians. Anyway, this is another subject, not the subject for today. But yeah, so at the same time, I got very much into coding and programming. I got in love with that. So I started developing this interest in informatics and how I could apply it in my day-to-day. So even before AI, in 2021, in my hospital in Barcelona, in the middle of the pandemic, we started changing the EHR, evolving the EHR, and I got involved into that. I actually developed an application that is, I developed it myself and then was integrated in that EHR, which at that moment was called iLabs, which was a laboratory application. And then I did that. I finished my data science MSc with Diego. So I'm explaining all this because when I decided to switch from rheumatology to clinical informatics, it wasn't because of AI. It was because I thought that time that we first had to solve other things before using AI. And one of the things that I was convinced we had to solve was the EHR. So I got into a standard that I will talk about that in a few slides, which is called OpenEHR. I basically switched my career to try to improve the current EHRs so that at some point we could use AI safely in our EHRs. And this is basically what I will explain you today, how I went from this AI hype, which was me like 3 years ago or 4 years ago, like AI is going to solve everything, to a more grumpy man, which is me now, telling you that, well, let's wait a bit, let's solve a few other things before we implement AI. And basically, this is what I'm going to tell you and explain you today. These two sides of the coin with AI happened in several levels, and even with the big giant of AI, OpenAI, which is the main provider of LLMs, well, all the GPT models. Actually, their name is called OpenAI, but well, we now know they're not that open, right? And there's, well, to advance and to do these big models and these groundbreaking models, they had to do some things that might not be that good. So they are using massive infrastructure. And when I mean massive infrastructure, you cannot imagine how many data centers they need to actually train their models and how much CO2 they are creating because of training these models. Obviously, this also implies massive centralized costs. This implies centralized control. If you want to innovate with this proprietary, I would say, models, so these are GPTs, Claude, even Mistral, those that we don't know with which data they were trained, you are not able to actually improve them or make them bigger or make them more specific to your use case. And obviously, this has some lack of transparency behind it. So we cannot certify how they will act in each context. And this is particularly relevant in healthcare. And this is one of the reasons why we are using a lot of AI in our own, as Sergio said, you can use a model in your own PC, or even you can use the ones that are publicly available. You can use it in your smartphone. You can use it even in the computers you are using in your hospitals and centers. But I'm sure that no one here is using a full-blown LLM in their own EHR or a service connected to the EHR that is using a full-blown LLM hosted in the cloud. Because obviously, healthcare is different. We are special, and we need to acknowledge that because we're dealing with patients' lives and we're dealing with patients' data. And it's also a matter of responsibility. So I will try, obviously, I only have 20 minutes now, probably 10 minutes left. So I cannot dissect what are all the barriers the barriers that I think that are stopping AI to be implemented. But what I can do in the following 10 minutes is show you a few things that might change the way you see these models so that we can actually make this happen. And that at some point in our clinics, we will have this AI helping us, because AI is for good, obviously. I'm not criminalizing AI. I think it can be really useful, and Sergio has already demonstrated that. With a few prompting techniques, knowing how to use it, it can be really helpful, and it can take loads of work from what we do as clinicians. But we need to do it in a way that is scalable, so that everyone and all patients can benefit from it. So basically, these are more like reading recommendations. This is this paper in Nature Medicine that was out like a few weeks ago. I think it's a really good review on generative AI. So if you want to get into, apart from what Sergio has already explained, which was really good, if you want to get into it, and also it dissects quite well what are the barriers, just look into that. And if you are in a stage where you're playing around with LLMs or even traditional machine learning models, and you're trying to get your hands dirty, I think it's really good to read the AI Act, because not from a legal perspective, but it puts a framework where you can evaluate exactly what you need to have a robust machine learning or even more advanced model for healthcare. So this is more like reading recommendations. And now I really like this photo because the challenges in AI can be discussed basically with this image. I think you can discuss most of the things in life with this image. So this is a restaurant that says, we offer 3 kinds of service: good, cheap, fast, but you can pick only 2 of them. So basically, if you want a good AI and you want it fast, it won't be cheap. And this is what is happening right now in healthcare. So we have really good LLMs, which have demonstrated in the literature, like they can solve clinical cases, they can reduce bureaucracy. But if we want to implement these models in the whole healthcare system, so that all hospitals in your healthcare region, wherever you live, benefit from it, that won't be cheap. Definitely won't be cheap, because these models need massive infrastructure to run. And then you could put different scenarios like, well, if you want then probably cheap models that are good, then probably you will need to go the path that Sergio has already given a clue, is train your own models or reduce them so they are very specific, that you can run them in your infrastructure or in infrastructure in the cloud that you can pay, and then it will be cheaper. But that won't be fast, because you need to actually learn a lot about it and actually train them to be really specific in your own scenario. So you get how this framework works. So then we have another problem, which is our EHRs, right? I don't think there's no one in this meeting that will say that they love their EHR. And this is for a reason, because obviously digitalization in healthcare has been very heterogeneous in different countries, in different regions. And it's the same, it's so complex that we've done our best, but still it's a tool that is not helping us a lot. So imagine your EHR with an AI plugged on top of it. Probably, well, this to me looks a bit scary. So this is one of the things that I focus my day-to-day job to try and solve these problems with the EHR. So I'll give 4 ideas on where to put the focus when implementing AI. So there's obviously more than these 4, but I think these are the main ones, so that you can, well, think about it and see if that helps when it comes to implementing AI. So first of all, obviously, privacy. So this image is a data center. And this data center can be in your own hospital or in another place. So when it is in another place and you're connecting through the network to retrieve and to input information, this is what we call the cloud. So basically, most, at least in Spain, most of the hospitals have their own data centers, and now we are migrating slowly to the cloud because obviously we cannot maintain our own CPDs. But you need to be really conscious on where these data centers actually are. And normally, when you use the cloud in healthcare, you want a data center that at least is in the European Union, if you are in the European Union, and ideally in your own country, because of obviously legal reasons. But I'm telling you all this because if you're using, for example, ChatGPT, you need to be very conscious that all that data goes to data centers that are in the United States. And I think this is relevant to know because once I knew this, I was a bit more conscious on the data that I was inputting ChatGPT. That doesn't mean we shouldn't use the publicly available ChatGPT, but we need to be cautious on the data that we are inputting because it's good to know that this data is going to the United States. Then there's obviously other plans. You can have an enterprise plan where they assure you that the data won't be used for training. Then there's the Microsoft Cloud called Azure that hosts the GPT models, and they can be hosted in the European Union. I mean, there's exceptions, but just in a general manner, this is something good to know. So how do we solve this actually, if we want to use LLMs? And I gave a hint, and Sergio also gave a hint in his presentation. And this is something that is quite in vogue these days. We are now able to get these LLMs to be smaller models, so we can quantize them, or we can even specialize them that much that we can make them smaller when it comes to resource allocation, that can be run even in your own mobile phone. So this means that you could run it in your own infrastructure. And this is really good because you have control on where the data is going. And also you have control. So specializing these small language models also helps you have control on what is actually happening in that model. Another thing is sustainability, and it's also related to this resource needs of these big models. So it's also related to these small language models things. We need to be really cautious on how we use these LLMs. So for example, to me, it's a bad use to ask ChatGPT what will be the weather today, because obviously you're using a very big model to ask a question that you already know from your applications or just putting on the TV. This is an extreme example, but sometimes we use large language models for things that we can do it in another way that is more sustainable. And I think when it comes to healthcare, if we start using these models, we need to be very specific, and we need to constrain this model to specific tasks so that this is sustainable, not only from a cost perspective, from an economic perspective, which is something more related to what I've been telling you before, but also when it comes to the planet. Also, and here you can see both sides, AI can help you itself be more ecological and be more green. So you can use machine learning models or AI models to actually optimize how you use energy. So it has both sides. but it's good to take into account. This is probably the most problematic one in healthcare. So here's an example we could use, even the sentiment analysis example that Sergio showed us. So imagine we have an application that is analyzing the comments by the patient, or this abstract that was presented in ACR last year, where they presented an application that was a coach for lupus patients so that they could ask questions and they had response. This is really good. I mean, it's a really good use of AI, but imagine that a patient asks for critical help through this application, and the application, well, at that point, because obviously LLM models don't give you deterministic responses, you cannot control I mean, you've got tools to control it, but there's a small percentage that you cannot control. Imagine that this application tells the patient, "Oh, this is okay. What you're telling me is not critical. Stay at home," and this patient dies. Well, this is really extreme. But who takes responsibility for that, right? This is something we need to solve from a political perspective, from a legal perspective, and from an organizational perspective. So this is something that we still need to solve in healthcare to actually implement this type of models. Obviously, there are several risks, and this is also really well put into the AI Act. Also, we need to, in some cases, and I told this before, we don't know what was the training data. We cannot account for what these LLMs will tell if we're using it in a medical setting, right? And these are some examples from, well, obviously these models were trained with loads of data and history in general, well, encompasses gender stereotypes, encompasses racism, etc., etc. So when we're using it in this setting, when we obviously need to preserve this human rights, well, obviously we need to have this type of accountability to be transparent, and this can be solved with training your own models and make them specific to your use case. And then this is, well, one of the other big barriers, which is scalability. So I'll be brief here. Imagine you can put it into your own system. I'm sure that in some countries, you have an hospital and a primary care setting lying in the same geographical place and still use different systems. And each system has their own database, has their own application, and has their own logic. And if you want to connect these systems, you need to basically create cables to connect one to another, but obviously map each data point to each data point. And this is obviously really resource intensive. Imagine that you develop an AI system, an AI algorithm. It won't scale until you align all this. I mean, if you train your own EHR in your own setting, then this doesn't mean that you can plug and play in another hospital. So you will need to do some adaptation so that it works there. So what OpenEHR, which is an open community, an international community, and some thought leaders have proposed is this open platform vision, which is something that we are running here in Catalonia, in Spain, is to have a common data layer. So a common repository of clinical data that is unique, that there's clinical consensus, and that everyone is using this normalized data layer. And then on top of that, well, you can connect AI to get some insight, but you can also connect all the different applications with the premise that everyone and all applications and all data products save the data in the same way. So this is what is called standards, because in the end, you have this type of problems. Even with one medication, you will have different applications, and you have different ways on how to save this data. Obviously, you could save it by the commercial name, even the dosing. You can save it in different units. So imagine you have an AI algorithm that uses this input as a feature. Each time you want to scale it and implement it in a different setting, you will need to map this data. So one solution, and this is what I'm working right now, is standardizing all this data so that then we can plug and play these algorithms or whatever. Also, we need to take into account that there's this thought and this thinking that LLMs and generative AI is making clinicians dumber. And this has been demonstrated in a recent paper where they can certify and that they've been able to show that there's that the endoscopists are de-skilling after exposure to artificial intelligence. And this basically, we need to be careful on how we use LLMs for clinical reasoning and how we train ourselves to preserve our own way of clinical reason. Also be careful on what it's called illusion of understanding. So LLMs can make us very powerful, very knowledgeable, but that doesn't mean that we actually integrate all this data in our own thinking. And then obviously all this cognitive effect and changes in the society, which is another completely different subject. So these are my last slide. I think I've said most of the key messages. AI is for good. We need to make it good. So this is our mission right now. So I think there's several people in the rheumatology community publishing and educating a lot about AI. Now we need to actually make it happen, and it's up to us. This, in my opinion, goes through solving other things that are not as sexy as AI. So one of the things is data standardization, EHR optimization. But obviously we are in a sweet spot, and we have the tools where we can transform this menaced health system with technology. So basically we need you. And I hope I'm happy to take messages through email, through LinkedIn. If you think if it resonates with you, if you want to help in the open EHR community, whatever, I'm happy to get you in. So that is all. Thank you.
Thank you all for the great explanations. I think that we are now reaching the closure of our webinar. I would like to remind everyone to please don't forget to fill out the evaluation survey that will be sent to you by email. It's really essential for helping us to improve future webinars. Thank you everyone for joining us and for the great presentations, and Emmanuel for co-moderating it.
Thank you all. Thank you, Sergio. Thank you, Xavier. Thank you, Andrea, for joining us here today. And thank you all for listening and being here with us and making everything happen. Thank you very much.
Thank you.
Thank you.
Bye-bye.
Bye-bye.